Welcome to the deep dive. We're here to, cut through the noise and find those aha moments, especially in tech, like programming. It's easy to feel a bit overwhelmed, right? We all want ways to grasp things faster, not just skim, but really get it. So today, we're doing a deep dive into generics in Java. This isn't just a minor feature. It's really key for flexible, reusable, and importantly, type-safe code. Let's try an analogy to get started. Think of a box, okay? A really versatile box design. Initially, maybe it can hold anything. Books, toys, electronics, whatever. But what if you want this specific box to only hold books? Generics are kind of like that. They're the reusable mold, but when you make the box, you put a label on it, a really strict label, like books only. And it actually stops you from putting a toy inside. Right there.
Yeah.
So our mission today, unpack what generics are, why Java even needed them, how they actually work, and the huge benefits they offer for cleaner, safer code. Think of this as your safety net for understanding generics. Okay, so let's rewind. Before generics, what was Java programming like then? It sounds a bit chaotic.
Chaotic is a good word for you. A bit like the Wild West, maybe. Before generics, Java collections, things like array lists, they were very non-specific. They could hold literally any type of object.
Anything. So you could just mix numbers and text and whatever else.
Exactly. Integers, strings, your own custom objects all jumbled together in the same list. Sounds flexible, maybe.
Flexible, but I can already sense the danger. That sounds like it could lead to some real problems down the line.
Oh, absolutely. The biggest pain point was runtime errors. Big ones. Because nothing stopped you from adding, say, an integer to a list you thought only contained strings. The compiler was fine with it.
So the check wasn't happening up front.
Right. Then, much later, maybe deep in your program's logic, you try to pull an item out expecting a string, and bam, you get an integer instead. Class cast exception. Your program crashes.
Ouch. And finding that bug must have been difficult.
A nightmare. Especially if it only happened in production. A huge productivity killer tracking those down.
And I bet the code itself wasn't pretty either, trying to prevent this.
Exactly. You had developers writing tons of manual checks. Lots of instances of followed by explicit casting.
So pull something out, check its type, then convert it, just to be safe.
Yep. Every single time. It made the code really verbose, cluttered, and just plain hard to read and maintain.
And easy to mess up, I imagine.
Very easy.
Yeah.
Introduce one wrong cast, and you've got a subtle bug that might take ages to find. The hidden costs were massive.
Okay, so that paints a pretty clear picture of the before. A bit messy, error-prone, frustrating. Generics, then, must have felt like a breath of fresh air, bringing some much-needed order.
A huge breath of fresh air. It was a fundamental shift, really. Like you said, it brings order. It allows you to shift error detection left, as they say.
Shift left.
So you catch the errors much earlier in the process, during compilation, before the code even runs.
Instead of waiting for that runtime crash.
Exactly. So fundamentally, generics are this Java feature for defining classes, interfaces, methods that operate on types specified as parameters, giving you flexibility, reuse, and that crucial type safety.
So how do they nail those problems we talked about? The runtime errors, the messy code. It's that label on the box again, isn't it?
It really is the perfect analogy. Generics let you declare the intended type. You can say list string, and that's a contract. This list only holds strings.
And the compiler enforces that contract.
Rigorously.
Yeah.
If you try myStringList.add 123, the compiler immediately says, nope, that's an integer, not a string. Error. Right there.
Okay, so that's how it stops the runtime errors. It catches the mistake way earlier.
Precisely.
Yeah.
Compile time, not runtime. That's the magic. Mistakes found early before they cause real damage.
And the messy code, the checks and casts.
Gone. Vanished. Because the compiler guarantees that if you have a list string, anything you get out of it is a string. No need to check, no need to cast. The code becomes dramatically cleaner, shorter, easier to understand.
And the reusability part.
Huge win there, too. You write one generic list interface, one array list class, and it works safely for list string, list integer, list customer, whatever type you need. One design, multiple safe uses.
That's incredibly powerful, safety and efficiency combined. But, okay, let's get into the nitty-gritty. How does Java actually do this? What's the mechanism?
It's pretty clever, actually. It works using something called a type parameter. Think of it like a variable, but for a type.
A variable for a type. Okay.
Right. So when you define, say, a generic class, like our box, you use a placeholder, often just T. So you'd write class box T. T just means some type that will be specified later.
So the blueprint itself isn't tied to book or toy yet. It's just ready for a type.
Exactly. Then, when you use the box, you provide the actual type. That's called instantiation. So you write box book, my book box, new box, or box toy, my toy box, new box.
Ah, so that's where you lock it down.
That's where you lock it down.
Yeah.
And from that point, the compiler enforces it. It checks at compile time that you only put book objects into my book box and only toy objects into my toy box.
It's tried across the streams and the compiler stops you.
Stops you dead in your tracks long before the program runs.
That shift from runtime to compile time checking really feels like the core benefit, doesn't it?
It's absolutely central. It prevents bugs, saves debugging time, makes refactoring safer. It's a huge improvement in the development cycle. And this same generic box T code works seamlessly for box string, box integer, anything. That's the reusability.
And you see this mostly with collections, right? Like list and map.
That's definitely where beginners encounter it most. Listy, MapK, V, the collections framework relies heavily on generics, but you can absolutely use them for your own custom classes, interfaces, even individual methods. They're very versatile.
Okay, this makes sense, but it does raise a question for me. If the compiler is doing all this checking, does that add overhead? Does it make the program slower when it actually runs?
Ah, that's a great question. And the answer leads to a really important, sometimes slightly confusing concept called type erasure.
Type erasure. Okay, what's that?
Well, basically, Java performs all those strict type checks during compilation, make sure everything is safe. But then, when it compiles the code down into bytecode for the Java virtual machine, JVM, to run, it mostly erases the generic type information.
Erases it. So the running program doesn't know it's a list string.
Largely, no. At runtime, it often just sees it as a raw list. The type parameter T might be replaced by object, or it's bound if you used bounded types.
Huh. Why do that?
Primarily for backward compatibility and efficiency. It means generic code can interact with older, non-generic code, and it avoids runtime overhead associated with carrying all that type information around. The safety net was the compiler's job.
So compile time safety, runtime efficiency, got it. It does sound like there are subtleties there, though.
There are. Type erasure explains why you can't do certain things, like directly create an array of a generic type, new T, or check instance of with a generic type parameter directly at runtime sometimes. But for most uses, it works seamlessly.
Okay, so generics aren't just one thing. You mentioned classes, methods. What are the different flavors we might see?
Right, they show up in a few key forms. You have generic classes, like our box T, a blueprint that takes a type parameter.
The reusable mold idea.
Exactly. Then there are generic methods. These are individual methods where the type parameter is declared just for that method. Think of a utility method, maybe a sort method, that can sort any kind of list integer, list string, whatever, as long as the elements are comparable. You write the sorting logic once.
Ah, so the genericity is scoped just to that one method.
Precisely. And we also have generic interfaces. The collections framework is full of these. ListC, MapK, V, comparable T. These define a contract that implementations will adhere to using specific types.
Makes sense, like a blueprint for behavior that works with different types?
Yes. And one more important variation is bounded generics.
Bounded, meaning you restrict the types.
Exactly. Sometimes you don't want your generic code to work with absolutely any type. Maybe it only makes sense for numbers or things that can be compared, so you can set a bound, like T extends number or T extends comparable T. This says T can be any type as long as it's a subclass of number or implements comparable.
Okay, that adds another layer of control. And where do we see these used most often in practice?
Oh, definitely. Collections. List user, map producted, product details. That's bread and butter Java. Also, building reusable utilities and algorithms, like that generic sort method, or maybe a generic function to filter a collection. And of course, building flexible components or classes in larger systems like containers, data holders, things like that.
For someone learning, though, collections are the main starting point.
Absolutely. Get comfortable with array list string and hash map integer, customer first. That covers a huge amount of ground.
Right. So we've gone from the Wild West to this structured, safer world thanks to generics. Let's wrap our heads around the big advantages again. What are the real payoffs here?
The payoffs are significant. They really change how you approach coding in Java for the better.
Okay, number one has to be type safety.
Right.
Just preventing those wrong type errors.
Absolutely fundamental. No more class cast exception surprises at runtime because you put the wrong thing in a list.
And that leads directly to cleaner code, doesn't it?
Directly. All that instance of checking and manual casting just disappears. Your code becomes much shorter, more focused on the logic.
Then there's reusability. Write it once. Use it for many types.
A massive saving in effort. One array list works for strings, integers, customers, anything safely. Less code to write, less code to maintain.
And it makes the code easier to understand. Readability.
Definitely. Seeing map order details tells you exactly what that map is for, right in the type signature. It's self-documenting to an extent.
And we keep coming back to this, but early error detection, finding mistakes at compile time.
It's arguably the biggest practical benefit day to day. Catching errors while you're coding, not weeks later when a user hits a bug, saves so much time and pain.
And all this adds up to just more flexibility, creating code that can adapt.
Exactly. Robust, adaptable code without sacrificing safety. So, given all that, how do you actually get started comfortably?
Yeah, good question. If you're new to this, my advice, start with collections. Seriously. Use arrayless string, hashmap integer, string, get a feel for it. See the errors when you try to misuse them.
Solid advice. Experimentation is key.
And use meaningful type names when you define your own if you get there. Don't
Right.
just use T everywhere if element or key type is clearer.
Good point. Clarity helps.
Build simple examples first. Don't try to build some super complex bounded generic thing on day one.
Walk before you run.
Exactly. Just think of them as making things flexible and safe. That labeled box, it holds what it says it holds, guaranteed by the compiler.
It really is that powerful combination. Flexibility meets safety. It makes Java development more reliable, more efficient, and honestly, less frustrating.
So there we have it. Generics really did change the game for Java. They took a potentially messy, error-prone situation and introduced structure, safety, and reusability. They make working with data simpler, clearer, and well, less likely to blow up unexpectedly, which is always nice. As we finish up, maybe think about this. The ideas behind generics, designing for flexibility, ensuring safety through clear rules, achieving clarity, these aren't just Java concepts, are they? Where else do you see this? Think about systems or processes in your own life or work that use templates or strict labels to manage complexity and prevents errors. What other labeled boxes help bring order and safety to potentially chaotic situations? Something to mull over.